Welcome to the Transport and Mac session. I am Michael Garry, Head of Content for Atmosphere, and I'll be moderating this session. We have three excellent speakers to discuss refrigerated transport and mobile HVAC. Each speaker will have up to the Transport and Mac session. I am Michael Garry, Head of Content for Atmosphere,
I'm hearing an echo
and I'll
myself.
be moderating this session. We have three excellent speakers to discuss refrigerated transport and mobile HVAC. Each speaker will have up to
Michael, please shut the swap card.
What?
Shut the swap card application, please.
Hearing an echo. And I'll be moderating this session. We have three excellent speakers to discuss refrigerated transport and mobile HVAC. Each speaker will have up to
Michael,
Yeah, I'm doing it right. I'm doing it right now. Hold on. Sorry. Okay. All right. Let's start that again. I want to welcome everyone to the Transport and Mac session. I'm Michael Garry, Head of Content for Atmosphere, and I'll be moderating this session. We have three excellent speakers to discuss refrigerated transport and mobile HVAC. Each speaker will have up to 15 minutes to speak, followed by 1 to 2 questions. That will leave time for Q&A at the end. After this session, there'll be a 10-minute break, followed by the final parallel sessions in heat pumps and case studies. Don't forget to put your questions, if you have any, in the question box on the screen. So without further ado, I will introduce our first speaker, who is Lukas Beier, R&D Manager for TEKO Refrigeration. And a little bit about Lukas. He started his apprenticeship at TEKO as a mechatronics technician for refrigeration in 2013, then worked in TEKO production as a mechanic for a short period before beginning his studies as a Bachelor of Science, specializing in refrigeration technology. Since then, for more than 2 years, Lukas has been a member of TEKO's Research and Development Department. So without further ado, I'll turn it over to Lukas. Is Lukas on the
Yes, I will share my screen.
Okay.
1 second.
Thank you.
Klicken auf die Präsentation, bitte. Yes, okay. So my presentation is about border kitchen sustainability equipped. And first I want to start to thank you all to visiting my presentation. And we all know there was a great upheaval in recent years in terms of refrigeration technology. The popularity of CO2 has risen sharply, and CO2 is finding more and more uses in different applications. Currently, applications in the area of railway transport are also interested in using CO2. So our CO2 unit, Rockstar Train, is one of them. Rockstar Train is one part of our CO2 series, which is called Rockstar. The project Rockstar Train was a cooperation between the company TEKO and Siemens. The project of this cooperation was called Valero MS. At the beginning of this cooperation, we have to talk about the applications which we use for a board kitchen, which you can see on the right picture. It's a typical board kitchen of a train. So the first fact is that we need for this application a capacity range up to 1.5 kilowatts. This capacity we need in LT and empty applications. The capacity is split in 5 different types of cooling points, which you can see also in the picture on the right side. In the lower part, you can see a dispenser, which is in a board kitchen used for beer or soft drinks. Next to them on the right side, you can see a drinks drawer with a showcase on top. Next to the showcase, you can see a twice cabinet this is a freezer and a drinks fridge. At the back of the border kitchen, you can see a triple unit, and this is a fridge for trolleys. In this project, we have also various specifications and specific guidelines. These guidelines are, for example, limited dimensions or limited amount of air. Another point was a specific material, stainless steel, which we have to use for the complete unit. The refrigerant CO2 and the sustainability for railway applications was also very important because it's a topic guideline. Two hard guidelines were the fire protection and the vibration test guideline. For example, this vibration test lasted 6 hours, and the vibrations were simulated in 3 axes. These tests could simulate a time of 25 years in operation. So with this test, it was good to see how our products use after hard shocks or very intensive vibrations. For example, pressure switches or other electrical parts are mainly interesting to know how they work. Following, we are looking for a solution and an implementation. So we choose the Panasonic hermetic rotary compressor for this application. And this compressor works with a 2-stage compression. The refrigerant, as I told, is CO2. And this compressor is also speed controlled by an inverter. Let's talk about the main function of this 2-stage compression. The 2-stage compression of this Panasonic compressor is as the suction line is on the left side. There are 2 suction pipes, and on the right side, there are 2 discharge lines. The first suction line is a typical suction line which comes from the different cooling points of the whole system. This suction gas is compressed in the first stage, and the discharged gas isn't go out directly. It serves the compressor cooling inside of the shell. After the compressor cooling inside of the shell, the compressed gas streams out of the discharge 1 line. This discharge 1 gas streams through a desuperheater, and there we cool the desuperheated gas. At the outlet of the desuperheater, we create a mixture out of flash gas and desuperheated discharge gas, and this mixture is inserted in the suction 2 line. The second compression stage is a direct compression. So we have an inlet in the second stage and an outlet directly to the in and outlet pipes. After the second compression, we have the typical hot gas line. This hot gas line this hot gas stream is now very hot, and we have to cool it. In this unit, we choose an on-top gas cooler. This gas cooler is placed next to the superheater, so we have the completely heat exchanger on top of the unit. In this unit, we also use a variable speed gas cooler fan and a temperature controlled desuperheater fans. The desuperheater is in front and the gas cooler is in the back. The airstream in this application goes from the front. On the right side, you can see a side glass with a yellow and green part at the front. There the air goes in, streams over the individual parts, cools these individual parts, and goes from the bottom in the heat exchanger and on the top of the fans out. Also, this unit has a very compact design. This compact design has the advantage that we could install it in very small spaces, which was also a guideline in this project. The electrical installation is quite easy because the whole connection cables are with plugs. So you have to put the unit in the slide, connect the plugs, put it completely in. And after this, you only have to connect 2 external wires at the front of the desuperheater. This unit also has only a high pressure valve, so we don't need a middle pressure valve. And the refrigeration receiver, the refrigerant receiver, is approximately 2 liters in the capacity. The safety valve has 90 bars, and we also have removable side and front panels. The reason for these removable front panels and side panels is the accessibility of the individual parts. As you can see on the picture, the piping and the individual components are very close together, and that makes it very hard to work on these individual parts when there are no panels at the outside, because then you have to remove the gas cooler and the desuperheater. So with these removable panels, we also added noise reduction insulation and anti-boom mats. These anti-boom mats are placed in the side panels and the back panel, and the noise reduction insulation is in the front panel around the side glass at the front. The reason for these mats and this insulation is because we are in the passenger transport, and there we have to reduce the noise of a unit very hard. Now we'll take a picture where the unit is used. This picture shows a typical board kitchen in a train. Now we're in the passenger area, and that's a bar where you can order your food or your drinks. The next picture, there we can see the inside of the galley. The galley is also called for the kitchen. This picture shows on the back of the corridor 2 doors, which are on the bottom. And these 2 doors are the trolley cooler, the trolley fridge. And over this trolley fridge, on top, there are 2 panels. These 2 panels are removable. And in the back of these panels, there are the slides where we can put the Rockstar train in. In such a kitchen, there are used 2 Rockstar trains. One Rockstar train for smaller empty applications and LT applications combined, and one Rockstar train especially for empty applications with a higher capacity. On this picture, you also can see some other inserts in this kitchen. On the right side, for example, the oven where you can warm up some food, and on the lower part, you can see these fridges which we run with our units. Okay, at the end, it's nice to see that the refrigerant CO2 isn't not actually only for big capacities and big units. It's only the use for smaller and I think units which have not the big space like a supermarket. So we have a lot of applications where we can use CO2. Thank you.
Okay, thank you, Lukas. That was really an interesting application on a train that we haven't seen very much before. Quick question. When was this unit installed in a particular train, and is this the first use of this system?
Of this CO2 system?
Yeah, on the train. Was it installed on a particular train?
Yeah, in trains there are always cooling units for the board kitchens, especially. But the CO2 unit we created, so the Rockstar train, is the first unit which runs with CO2.
Right, but has it been actually installed in the field on a train?
No, actually not. It's
okay.
in the pre-phase.
Okay, but that's your plan. Have you started to make it available?
Yes. We also started some tests, but it's not in the series.
Okay, so it'll be on the market at some point in the near future.
Yes, exactly.
Okay, great. All right, well, we'll have time for more questions for Lukas at the end of the session. Thank you very much. It's always great to see a new application for CO2.
All right, we're going to move on now to our second speaker, Dominik Radler, Chief Technology Officer for productbloks, and Nikolaus Skarabela, Energy Efficiency and Mobility Officer for Schachinger Logistik. Let me do a quick bio on these gentlemen. Dominik finished his master's studies at the University of Vienna in chemical and process engineering. He went on to work for a big OEM, developing a new system for transport refrigeration of long-haul trailers. After this project, he co-founded productbloks with the aim to develop transport refrigeration systems with hydrocarbon refrigerants. Developed product for light commercial vehicles, achieved certification at the end of 2020, and is now commercially available as the first of its kind. Nikolaus Skarabela, since 2000, who is the Energy Efficiency Mobility Officer for Schachinger Logistik. Since 2009, he's been working at companies as an expert for the mobility and energy sector. His responsibilities include the development and implementation of new concepts in the mobility and innovation sector, trainings and lectures, and the acquisition and project management of large lighthouse projects like Zero Logistics. With that, I will turn the stage over to Dominik and Nikolaus.
So now, I guess you can hear me now, right?
Yes, thank you.
Great. So thank you very much, Michael, for the introduction. I just saw that I forgot Nico to put in on the slide, so he will be presenting some information on the road test we did with our R290 transport refrigeration system. We installed on a battery electric LCV earlier this year and performed field tests with this system. And I want to show you what our findings were on these field tests and how the system performed overall. So a quick overview, what will come in the next 10 minutes. I will give you an objective and goal. I will talk briefly about the refrigeration system that productbloks has developed. I will talk about the vehicle we converted, and then we'll talk about the road tests and the outcomes. So the objective was to realize a zero emission transport refrigeration system and a transport refrigeration vehicle, actually. So both the vehicle and the refrigeration system should run on zero emissions when it comes to refrigerant and also the propulsion system. We also wanted to showcase with our system that R290 as a refrigerant for mobile application is technically and economically feasible. And therefore, we developed the productbloks HCB12 system. It's a sealed R290 circuit with a leakage rate of below 5 grams per year. We have 140 grams of refrigerant charge in the system. The 24-volt supply voltage can be applied to either internal combustion engine systems, but also, and this is how it's engineered, for the battery electric systems. When we talk about engineered for electric, we see that the main drivers and requirements for electric vehicles are quite different than they are for combustion engine driven systems or vehicles. So the overall weight of our system is 31 kilograms, which is 35% less than the next heavier system on the market currently. So we are by far the lightest systems. This is by far the lightest system, which is also a result by using R290 as a refrigerant with its high volumetric efficiency, and also by the lightweight design. We achieved plus 20% of part load efficiency. We have zero emissions on the system, so we have R290 with 5 grams per year leakage, so it's negligible CO2 emission or greenhouse gas emission. We have low noise, and we came to a minimum of plant maintenance, which is also important for users of battery electric vehicles, because they also have a very low plant maintenance or very low maintenance at all. The system we converted, so the van we converted is a Nissan ENV 200. That's the base vehicle. There is a variation of this vehicle called XL Voltia, The main difference is that with the XL Voltea, I hope you see my mouse, this top of the system is heavy, is higher, so they put in a bigger cargo space, providing a more practical cargo space in the end. We converted it to a refrigerated body. This is done quite conservative. The system has 40 kilowatt hours of battery, and after conversion, we reached the 300 kilograms payload after conversion. So the electric architecture that we chose is also some kind of special. The refrigeration system is supplied directly by the traction battery. So there is no additional battery needed for the refrigeration system. It is supplied directly via DC-DC converter, which is plugged to the battery of the vehicle. And this means that the user heads in the end does not need to maintain an additional battery, meaning charging, thermal management, all this stuff. Is not necessary. Of course, the cargo is slightly reduced due to the insulation, but still the remaining cargo space was enough for the customer we had in mind. That being said, I would like to hand over to Nico, who will talk to you about the road tests themselves, and afterwards we will talk about the conclusions and the data that we took of the road tests.
Thank you very much, Dominik. Yeah, Schachinger Logistik and me as a person, we were the project leader of the Zero project. We developed the van together with logistics partner like Achleitner Bierhof and Schachinger Logistik as well. Because we have, I think, 3 challenges in the logistics. It's one, to find driver, like you can see us in the UK. And that could be also a reason to go for electric, because it's more it's not that noisy. It's more just easy to drive. It's really just a nice vehicle. The second challenge, of course, is the TCO, total cost of ownership. Yeah, in logistics, it's all about costs, so the margin is very low. And the third challenge, of course, is coming more and more is sustainability. We got more and more requests from our customers to be more sustainable, and it's not only done with the electric vehicle, as we can see this. It's depending on this of the refrigerant of the vehicles. And we did some road testing as well as at the Biohof Achleitner. It's organic food provider, and normally he has organic food as a regional organic food, and then he provides us to the customers as the organic food as with the diesel van. And of course, as the customer don't like it really, as they want to get the food delivered CO2 neutral. Perfect. And this is how we go on, how we did it, and I think it was the best way you can do it is to go to the companies, just give him the first information to see how is the information standard in the company. And we did some analysis with software. So we logged all our cars with software, and then we can see how they go, how much payload is necessary, how much or how often is the door open, and so on. Then we have to do the evaluation what we can do is at the moment in this company, and then it's standard purchase. And like I said before, of course, we did not do it only as for sustainability. As it's not possible as to spend a lot more money and be the best sustainable company, but 3 years after as you're gone. So it's I think as you have to be sustainable, of course, with the cost, and it's possible. That's the reason why Bio of Achleitner's ordered some of the vans after the project, and also the Schachinger Logistik is looking for 15 cooled events for some part of the company. And then the next challenge is, of course, is the implementation of these events, because as charging infrastructure, you have to imagine it's a big problem as if you're going on a wider fleet. And also, I think as you have to mention is the fleet conversion. You have at the end, as you have maybe as the half of the fleet is electric, other half not. As you keep it in, you have to keep it in mind as in the process afterwards, until it's completely changed. Thank you. Dominik, können wir dich nicht hören?
Okay. So, thank
Sorry,
you.
can you hear me now?
Yes.
Yeah, perfect. I muted my microphone. So thank you, Nico, for the details on how we did it in the project. Over the course of the field test, we tracked about 250 parameters. So we generated a lot of data, and in the end, we condensed this down to some basic principles. So in the field test case we had with this fine delivery of parcels or of these bio or organic food parcels, we have about 5 door openings per hour, and even though these 5 door openings per hour is on average, we had a set point quality of 82%. So 82% of the times, even during these door opening phases or immediately after these door opening phases, the set point were within the acceptable tolerance of plus minus 0.5 degrees C. So the set point was 4 degrees C, and the acceptable margin was 3.5 to 4.5 degrees C. And over the course of such a route, on average, we consumed 7% of the battery capacity, which is a very important number, because this means directly the range reduction of the battery electric vehicle. So the combination of transport refrigeration and battery electric vehicles, they always have to keep in mind that the battery capacity is directly related to the range of the system, and then to the successfulness of the route, or whether or not you can successfully finish your route. During the field test, we had 0 operational failures. All of the routes were completed, and there is a number 0 CO2 emissions caused by the system, because we will see on the next slide that there's just one last source of greenhouse gas emissions left. So the 0 emission temperature control transport was shown. Renewable energy was used for charging, so that what photovoltaics on the premises of Bio of Achleitner were used to charge the system. A 0 emission transport refrigeration system was used, and the last source of greenhouse gas emissions was the HVAC system of the vehicle, which used R134A as a refrigerant. There was approximately 7% of range reduction caused by the transport refrigeration system, which is a pretty low number actually, which is also the reason for that is the high part load efficiency of the HCB12 system. And for the outlook, you could say that the new vehicle generations that are coming out this year, next year, with twice the battery capacity we had with the system that I presented to you today, even longer routes would be possible. And for example, for customers like such organic food delivery services, also for online grocery services, these ranges of these new vehicles are absolutely acceptable, and they are way higher than the range they would need for the normal emissions. And in the end, over the course of the project, the goal was to show that the 0 emission battery electric vehicles are both technically and economically feasible. And this was shown drastically, because in the end, we also showed that When it comes to total cost of ownership, Nico briefly mentioned it as well. It's right now it's already, depending on the nation you're in or you're operating in and the fundings you get, it's the economically right choice when it comes to total cost of ownership to go to a battery electric vehicle and to a zero emission transport refrigeration system. So that's for that. Thank you very much for your attention. If you have any questions, I think we can have one or two now and the rest at the end of the session, I guess.
Okay, Dominik, thank you very much. And thank you, Nikolaus, as well, for that very interesting presentation, talking about another natural refrigerant, R290, used in transport refrigeration. Couple of quick questions before we move on. So this has been implemented in the fleet of Biohof Schachinger, is that correct? They've implemented this in their fleet?
Yes, they used it in their normal operations.
Yeah, so they've already been using it as part of their operations. And
Yes.
So the system is available for other end users?
It's commercially available. It can be ordered.
Okay, great. And you mentioned that using 134A still for HVAC. Could the R290 system be incorporated for HVAC in this?
Well, we talked about this in the project, but this is just not an easy drop-in, because when you use R290 as a refrigerant, you have to really design the system when it comes to the flammability hazard. We did it without transport refrigeration system, obviously, but as a drop-in for the 134A system, it's not suitable. What we are discussing in future is probably to combine these two systems into one.
Okay,
but
great.
this is an outlook for the roadmap, so to say.
Okay, excellent. So that may be something in the future for HVAC.
Yeah, exactly.
All right, great. Thank you both again for that very interesting presentation of a system that's actually in the field and available for use in the field by others, and with the larger battery sizes, as you say, will become even more probably more interesting to the marketplace, right?
Definitely, yeah. Because one of the biggest issue with battery electric vehicles for these customers, Nico can tell you even more about that, is the battery size, and with that the range and the cargo load. These are the two limiting factors for battery electric vehicles, and also for the transport refrigeration systems that are applied to it.
At the end is a payload as well, as I say.
Yeah.
Great. Now, before we get to our third and final speaker, who's going to actually talk about HVAC in mobile in transportation, we're going to do a quick poll of the audience, which you can find on your screen in the sort of next to the chat and question box. And by the way, don't hesitate to enter any questions you may have for our speakers there. But the poll is, will a natural refrigerant ultimately be used widely in mobile air conditioning? Because as you know, mobile air conditioning mostly uses HFOs right at the moment. But will natural refrigerants ultimately be used in MAC? Yes, no, or maybe. We'll just take a minute to have people answer that poll question. And okay. And when we get the results, I will share them with the audience. Meanwhile, we have another question for product blocks. What is the cooling power of the system?
I anticipated the question. Yeah, the cooling capacity in the transport refrigeration system is measured by the ATP protocol most well, it's the mostly or commonly used standard, and with that we have 1,250 watts of cooling capacity at the 0 degree box temperature point. But this number, when you apply it to a battery electric vehicle, in the end, it's not the biggest factor or the biggest parameter, because for the battery electric vehicles, it all comes down to efficiency. So you have to design a system that is part load efficient in order to reduce the energy consumption, because before the battery electric vehicles were introduced with an internal combustion engine, the only difference an inefficient and efficient system made was that you have to come 200 kilometers earlier to the gas station, and then you can return to your route. With a battery electric vehicle, this is not possible anymore, because you only have one charge probably per mission, and you have to achieve your routes with this one charge. So efficiency is much more important than the absolute capacity, actually.
Okay, great. So I have the responses to the poll question, which was, will natural refrigerants ultimately be used widely in mobile air conditioning? And 89% of our audience said yes, and 11% said no. So pretty much pretty good endorsement for natural refrigerants coming in the future from our audience. So that's interesting. And having reported on that poll result, we'll move on to our final speaker, Bjorn Kern, Head of Technical Application Department for Konvekta, which does HVAC with a natural refrigerant, CO2. A little bit about Bjorn. Since 2005, he's been head of the Technical Application Department for Konvekta. His first project was a mobile transcritical R744 unit in 2008. Since 2012, he's been working on Konvekta's R744 heat pump generation 1 for electric buses. From 2015 till now, he's been supporting the transformation of Konvekta R744 heat pump generation 1 to generation 2, and the introduction in different customer applications. And with that, I'll turn over the floor to Bjorn.
Hello to everybody. So start to share my screen so that we don't know, is it work or not? No. Let's see. Yeah, we have it. Okay. Yeah. Okay. First of all, I would like to say thank you to have the opportunity to show something about Konvekta and about the mobile application, which we are using since many, many years in CO2. An experience would like to tell you something about of our experience of mobile heat pump, which we are using since many years in the application of battery buses. Some words about Konvekta. So we are established in 1957. We are in the center of Germany, and Hessen is a state. The country is Schwalbstadt, the city. We have some production lines in Barchfeld, which is in Thüringen, in Istanbul, in Turkey, and in China. And in total, we have 520 employees worldwide and 500 here in Germany. On the right side, you can see our building, which is called Test and Innovation Center. This one was built up in 2015 and is in operation in 2016. So there we can have we have a hall which is 26 meters long, can be shared in 3 units, and we can have an environment inside from -20 up to +50 degrees. We are testing the unit itself. We are testing complete vehicles. And we are working in our company in 4 divisions. We have the bus division, where we are doing AC and heat pump system for buses. We have rail applications. There we have this end of this year, beginning of next year, also our first R744 heat pump application on rails. We have cabins, which is horticulture and building machines, and we have the small business here with transport refrigeration here also established. This is the overview of our heat pump system, which is installed on a typical 12-meter electrical bus. We have here our rooftop unit, and behind the rooftop unit, we call this device energy carrier. The energy carrier module is thereon is the compressor. We have a chiller, warm water, chiller, cold water, inverter, and some other devices which are needed to have a good operation in CO2. And it starts from the compressor. We are going into this energy carrier module warm and taking out the first energy from the hot gas side into the water, which is distributed into the bus. In heating mode, we are going into heat side, inside heat exchanger. This is then the gas cooler. And the outside heat exchanger is working like an evaporator with an expansion valve. Just normal operation. And so we are collecting energy from outside and bringing it into the bus. Always this advantage here from our side that we are also creating warm water, which can be used always also somewhere inside the bus for any reason. In cooling mode, same one compressor, heat exchanger warm. We have the gas cooler outside, and we have the evaporator, which is giving now the cold energy inside the bus. And so we can change from heating to cooling by switching on and off valves like a normal heat pump operation. What we have here is a second loop. We have an expansion valve and an energy carrier module, chiller cold. There we are able to producing always cold water, independent what status the rooftop unit has. We are always able to producing cold water. In cooling mode, we are using that cold water to send that to the driver's place in order to cool this driver one. And in heating mode, we have the option to do energy collect. Energy collect is a mode which giving the bus manufacturer the opportunity to send wasted energy from the vehicle to this cold water, and we can bring it backwards inside the over the refrigerant process inside the bus. The now we can say it's a kind of networking between the heat pump unit and the bus. So I'm working many years for that one. In the beginning, the AC unit was put on the rooftop. We have one switch in the dashboard and maybe one knob where you can on and off. Meanwhile, is the AC unit completely connected with the bus, and especially with the vehicle control unit, which you can see like a own computer, which is regulate everything of that one. And we are giving, or we are trying to doing the complete thermal management from the passenger compartment, heating up from the rooftop unit over the chiller warm, cooling down, chiller cold water supply. With the warm water, we are feeding the side wall heaters here on the side, or the underseat heaters in heating mode. As I said before, with the cold water, we are feeding the driver's place for cooling and warm water for heating. And the controlling concept is complicated. We have to use in this such kind of system almost 12, sometimes 15 sensors, which are placing around the vehicle and collecting information, which will help us to control the system. The controlling, and that one becomes very, very important and is one key point of the success to have a good range of this vehicle. As I said, we are strong connected to the vehicle management. One example, for example, is the bus is driving. The state of charge is low. let me say 20%, but the demand of the passenger compartment is high, so high temperature inside. Then the vehicle control management said, okay, we have only a SOC of 20%. We need to save energy, sending us an information, and we are going into derating of the system. So the compressor speed will be derating so that we are saving energy. So this is very strong connected to that one. We are giving inputs to the vehicle management, and we are also receiving inputs to that. One example is that what I told, or in the morning, the buses needs to be preconditioning in the morning before they are going on the road. This is a typical signal what we are giving, what we are receiving from the vehicle management. This temperature control is very efficient. From these sensors, we are calculating power values, which are giving us an information about the compressor speed. Is the demand high or is the demand low? So, and all these elements, compressor and fans and blowers are able to controlling by the speed in order to have all the time the best COP for the complete system. The driver's area is an own place. The driver has always much more priority than the passengers inside the bus. In the public operation, the passengers inside are sitting there for maximum 30 minutes, but the driver has to work 8 hours on that bus. So high eye is always on the driver. It started now also that we are talking about with the customers to integrate a battery management system in our cold water loop and our warm water loop, which is also not so easy to do. But we are thinking that we can do the step next year, and then we have the complete thermal management of the bus under our hands. Preconditioning in the morning, it really, there are some ideas in great cities like Berlin that they are monitoring the weather forecast in the morning, said, okay, tomorrow morning we will start at 6 o'clock with 5 degrees. That means we have to start preconditioning at 4:30, and then we are sending out for our control center a signal to all buses that they are starting at 4:30 with preconditioning. So this sounds like science fiction, but it will become, I think, in the next 2 years. Some ideas like this. It's always about energy management, charging, and so on. The energy collect mode, which is also unique here on our system, that's because we can do always cold water whenever we want. We are controlling air quality inside the bus. We are measuring CO2 level so that the fresh air intake and will be controlled. Fresh air for heating mode is just to see is the air quality good or not. And then we are taking fresh air inside to feel all passengers comfortable. Here is an interesting chart that we got this year on the 8th of February 21. It was a very cold week, and the buses in Berlin, for example, are equipped with a measurement system, very city, where you can see on the time where the buses are, what are the consumption at the moment. And there we checked 2 buses. One bus was equipped with a regular AC unit, so no heat pump. The heating was done with electrical heater, like in, I would say, traditional way. And the other bus was running with our heat pump system with the newest version of software. And the driving distance of both buses were around 140 kilometers. Mostly of the time they are charging in the, they have a charge time between 12 and 1 in the afternoon when they have a break. So, and the vehicles were not preconditioned. What you can see, the blue one is always the consumption that you have for the drive. The yellow one is the consumption for the additional consumers like steering pump or whatever, or air compressor for brakes. And here we have the consumption of the heating system. So the first column is just the bus which has no heat pump. And the other column is the bus which has the heat pump on the rooftop. So we have the consumption of the drivers the same, the consumption of the consumers are the same, but we see a huge reduction of consumption in the heating phase. This brings us to when we are calculating this into range, then the bus with a regular unit has in this environment was minus 10 degrees ambient temperature, a range of 114 kilometers, and equipped with our heat pump system, he can run 151 kilometers. So the total consumption of the heat pump system in this application is 1.53 kilowatt hours per kilometer. With the next steps, beginning of next year, we are quite sure that we can go under 1.4. So since on the end of this year, we will have just around 1,000 units electrical one R744 heat pump system on electric buses around Europe. The major customer at the moment is the city of Berlin here in Germany, but Hamburg, Wiesbaden, here you can see some informations where we are operating. But we have also applications out of Germany in Luxembourg, Netherlands, always Sweden, Austria, and so on. So customers are quite happy, and we think that it's going forward also next week. So we end of 21, we have 1,000 units in the field, and I think that end of 22, at least 1,800, when we are lucky, 2,000 of units in the field. We have also diesel buses, which has no electrical drive, also diesel buses in the field, starting in 2014. There we had the opportunity to have one compressor available from a company, Garry, but unfortunately they canceled the compressor, and so we are waiting for new opportunities to have a compressor available which can be run also with a diesel engine, open and I would say direct driven by a diesel engine. Here are some pictures of our production line. This is a look of the heat pump system. The gas cooler or the heat exchanger outside is a little bit bigger and higher, so that we have enough surface to exchange the energy with the ambient. The application range of this unit is minus 20 degrees ambient up to plus 43. So also usable in North Italy and also North Spain. And here we have some pictures of our production line. This is we had built up also a new hall where we have fully automatically testing procedure. The units will be built up, assembling. Then we are soldering all the points, and then we are bringing each unit into such kind of chamber. All the unit will be connected to a high pressure system, and then the automatic check, all the tests that we are needed according to nomination EN 378 will be done automatically. It starts with high pressure 160 bar, has to stand under these conditions for 30 minutes. Then we are decreasing the pressure. Then we are doing leakage test. The test procedure of each unit is around 1 hour. And after 1 hour, we are sure that everything is running well and we have no leakage. And the unit can go with a good feeling to the customer. Here are some pictures of the typical application. Here we have the yellow ones are the yellow fleet in Berlin. The two customers where we have the most operation at the moment is Mercedes-Benz or EvoBus in Mannheim. And the other customer is based in Poland. It is Solaris. And also here with Solaris, we had also the first steps with R744 heat pump system starting in 2012, which was called our generation 1. But really around Europe, we have different kind of charging systems, plug charging, or this is called opportunity charging. The buses where we sent to winter test to Finland and Sweden, so everything was tested as under the leading of Mercedes-Benz. We have also some response here from the customers that BVG is Berlin operation set is an innovative system. We starting with them with the first buses in 2008. So they know us for a long time. They know the CO2 applications. Oh, what's that? Yeah. And the other one is NIAC, which is in the west of Germany. They have also CO2 systems here, and they are very happy with the maintenance situation. They have less maintenance. It's easy for handling, and everybody liked that one. And so they very interesting in this technology. So thank you for that one and for the time for listening to me. And I'm very happy to introduce you some application of Konvekta in case of CO2 heat pump. We can't hear you, Michael. You're quite. You have mute. Yeah, no. Okay.
Yeah. Okay. We have to wrap up our session. It's going to cut off in about a minute. So I want to thank our speakers and thank the audience. I hope that the audience found this valuable. And if you have any further questions, please address them to the speakers individually. Thanks, guys. Appreciate it.
Thank you very much. Bye-bye.